course on concurrent
This
programming.
meeting is being recorded.
Today's session is going to be on implementation of concurrent data structures, which is going to be very interesting. From my personal experience, I think this is one of the very interesting topics in overall parallel programming, which is going to be conducted by Dr. Praveen. Is Dr. Kalyan also going to be talking about it, Dr. Praveen?
Today, I would like to take the whole session.
Okay, sure. So without further ado, I hand it over to Dr. Praveen.
Thank you, sir. Thank you very much. Hi, good evening to one and all. On Thursday, we discussed about concurrent linked list implementation. Yes, in that session, we discussed about how to implement a concurrent linked list by considering different synchronization techniques. They are coarse grain synchronization, fine grain synchronization, optimistic synchronization, lazy synchronization, and non-blocking synchronization. Yes, today I would like to discuss about few more concurrent data structures. Okay. Yes, today's session, first I would like to discuss about how to implement trees. Later, I'm going to concentrate on concurrent hash tables. Finally, I would like to discuss concurrent skip list. Yes. Yes, when we look at the concurrent implementation of a data structure, okay. Yes, in a shared memory environment, a data structure which supports concurrent execution of all the basic operations, such type of data structures are called concurrent data structures. You have some idea about that. Yes. First of all, I would like to discuss what are the issues with the concurrent implementations. Okay, we need to take care of some of the things. To explain that, okay, I consider a very simple example. With the help of that example, I would like to explain the issues with concurrent implementation. Okay, right. Suppose we have a binary search tree. All of you know the definition of the word binary search tree. Okay, when you look at the definition of the word binary search tree, a tree which satisfies the Bst properties. What are the Bst properties? All the elements in the left subtree less than the root node, all the elements in the right subtree greater than the root node, left subtrees and right subtrees both should be the binary search trees. Okay, right. When you look at this particular diagram, figure 1a, that is a simple binary search tree with the keys 2, 4, 6, and 8. Okay, suppose consider. Yeah, that is in shared memory environment. Two threads, T1 and T2, both are going to work on that particular shared data structure. T1 is going to perform such operation and T2 is going to perform remove of 4 operation. So assume that T1 is started ahead of time. Okay. Yes, the job of T1 is it is going to search 6. Where is 6? When we compare the root node, okay, 6 is greater than 4. When 6 is greater than 4, yes, T1 try to search for the required value in the right subtree. Then in that process, okay, T1 reaches to the node 8. Okay, once it reaches to the root of the right subtree, T1 is going to be suspended because of some reason. When T1 is suspended because of some reason, okay, T2 starts its operation and T2 completes its operation before T1 is going to be resumed. In that context, what is going to be happen? Here T1 performs, T2 is going to perform remove of 4. When it tries to remove 4, yes, 4 is a non-leaf node with the 2 children. In that context, that particular node is going to be removed and that node is going to be replaced with minimum of right subtree. Here minimum of right subtree is 6. So when it is replaced with minimum of right subtree, then resultant binary search tree is shown in figure C, figure 1C, right? Now T2 is finished its operation. Yes, once T2 is finished its operation, now after that T1 is resumed. After that T1 is resumed. When T1 is resumed, in that context, whether it faces any issue, any problem, whether it faces any problem, yes. When you look at figure C at that particular instance, okay, what can you observe? You can observe that T2 completes its operation and T1 is in suspended state. Okay, after some time, you assume that T1 is going to be resumed. When T1 is resumed, what will happen? T1 is looking for search of six. T1 is looking for 6. Suppose if we use simple normal BST traversal, then what will happen? T1 returns an unsuccessful search. T1 returns an unsuccessful search. But that should not be the case, right? When you look at that particular tree, you can clearly see that 6 is present in the tree. But T1 returns an unsuccessful search. How can we overcome that particular problem? How can we overcome that particular problem? Please unmute yourself and give.
We can put logs like the linked list.
Okay, where can we put the logs?
Maybe the head itself, like the root.
Okay, if we put the lock at the root, then it seems to be a kind of a coarse grain synchronization, right?
Yes, sir.
If it is a coarse grain synchronization, in the last session, we observed that we got very less throughput.
Yeah, so maybe some fine grained type we can do maybe.
So even though if we use fine grain synchronization, what will happen? Suppose assume that T1 performs the such operation without acquiring any logs. Okay, we saw that how to write particular routine without using any logs. We discussed in the lazy list implementation, right? By creating an extra field, okay, we achieved that in linked list implementation. Okay, here actually assume that T1 such operation is a lock-free operation and remove operation is a lock-based operation. In that context, what will happen? T1 is a lock-free operation. In that context, without acquiring any locks, T1 can comfortably reach to the node 8. Okay, once it reaches to the node 8, it is suspended because of some reason. Okay, once it is suspended, T2 starts its operation. Again, in that particular process, anyhow, assume that T2 is a delete operation. If T2 is delete operation, it acquires the lock on some set of nodes. Okay, once it performs the required operation, it can comfortably release the logs. Assume that T2 completes its operation and releases the logs. Then how T1 knows about that operation of T2? Did you get my point?
Yeah, yes, sir.
Yes. Okay. Here in this context, usually when we look at the trees, okay, we are thinking about a tree ordering, right? What is a tree ordering? We are going to maintain a left, right, and parent fields information, right? In the usually when we want to create a tree, we are going to create a tree with left, right, and parent field information. Okay. Along with that, okay, we can maintain some other information also. What is that? That means when we consider the binary search tree, there are many different traversal techniques are there, right? Suppose if you traverse the particular binary search tree in order fashion, what do we get? Suppose if we traverse the particular binary search tree in order fashion, what do we get? In order means left.
In this ascending order, the sorted.
Yeah, in sorted order. If it is in sorted order, then we can handle all such type of rotations, right? Suppose if T2 performs the delete operation, then structure of the tree is going to be changed here, right? When the structure of the tree is changed, suppose T1 wants to find the 6. Okay, in that process, now where T1 is going to be terminated, T1 is going to be terminated at node 8. Suppose if you don't maintain any logical ordering or in-order traversal of the tree, then T1 is going to be terminated at node 8 with unsuccessful search. Suppose if you maintain the logical ordering among the nodes, okay, that means in-order traversal of the nodes, then T1 can look for its predecessor. T1 can look for its predecessor. When it looks for its predecessor, T1 can comfortably identify the required node. Are you with me? Are you with me?
Yes, sir.
Yeah, in that context, suppose here T1 observes the unsuccessful search by using tree ordering layout. When it observes unsuccessful search by using tree ordering layout, then in that context, it is going to verify structural changes in that particular process while T1 is doing the particular required operation. How it is going to handle those structural changes? It is going to be handle those structural changes by using logical ordering of that particular tree. Logical ordering means by using in-order traversal. In-order traversal means here for each node, we are going to maintain predecessor and successor information. If you maintain predecessor and successor information, we can clearly handle all those cases. In that context, T1 ends with successful search. T1 ends with successful search. Here you can find that when we use the logical ordering, T1 ends with successful search. Suppose if we don't use the logical ordering, T1 ends with unsuccessful search. So this kind of implementation is wrong. This is the correct in the context of concurrent implementations. So suppose if you want to do the concurrent implementation, along with the normal layout, we have to consider some other layouts. Here, what we considered logical ordering layout of all the nodes. Here we consider logical ordering layout of all the nodes. Right. Next. Did you understand the importance of logical ordering?
Yes, sir. Okay.
Yes, sir.
Okay, right, good. Next one. Okay, in this session, first I would like to explain about one particular data structure that is a kind of a tree data structure. Okay, in the first session also, I gave the definition for the tree, right? Okay, when you look at the definition of the word tree is a collection of nodes where each node contains the key and priority. Okay, yes, when you look at the this particular tree data structure, where each node consists of key and priority. When you look at the keys satisfies the Bst property. Next, and heap order property here, this one numbers satisfies the max heap property, either max heap or min heap. Here we are going to consider max heap property. So this particular tree, it satisfies both the Bst property and heap order property. So that is why this is called a tree. Okay. Why do we need a tree? Why do we need tree? Yes, usually for BSTs, okay, we need to write explicit height balance routine, okay, to achieve strict height balancing condition at each non-leaf node. Here, when we consider tree data structure, there is no need to maintain strict height balancing at each non-leaf node, but on average, okay, we'll get that we can observe that log and height. Okay, therefore, all the basic operations can be performed in log and time. That is the advantage of tree. Here, our interest is not the definition of this particular tree data structure. Here, our interest is how can we build concurrent trips? How can we build a concurrent trip? That is our interest. Right. When we look at the definition of the concurrent trip, what is the definition of the concurrent trip? Okay, in a shared memory environment, a trip which supports concurrent execution of multiple threads of computation is called a concurrent trip. Okay, right. Suppose there are few threads. Each thread is going to perform some operation. In that context, if threads are not overlapping each other, then there is no problem at all. If threads are overlapped each other, okay, then we have to handle such type of cases. How to handle such type of cases, I'm going to discuss. Yes, suppose if threads are overlapped each other, then what do we get? We'll get the problem of data race. Okay, to avoid those data races, we need different synchronization primitives. Okay, by using those synchronization primitives and any one of the synchronization techniques, we are going to address that particular problem. Next, before going to explain the concurrent operations on a tree, okay, first of all, I would like to explain how can we perform basic operation, how can we perform sequential operation on a tree. Later, I would like to discuss concurrent operations. Suppose consider this is a tree. Suppose if you want to insert a node into the tree, if you want to insert a node into that particular tree, how are you going to insert it? First, a node is inserted into a tree by using Bst property. A node is inserted into a tree by using Bst property. After that, we are going to verify whether that particular node satisfies the heap order property or not. If that particular node, newly inserted node, does not satisfy the heap order property, then what we have to do? We are going to perform some number of left or right rotations until heap order property is going to be satisfied. In that way, we are going to perform insert operation on a tree. Suppose consider an example. Okay, all of you, this is a tree. I already discussed this particular one. Here our objective is we are going to insert this particular one W comma 60. This I want to insert W comma 60 into this particular tree. Okay, as per the discussion, how this particular node is going to be inserted? This particular node is going to be inserted with the based on the Bst property. Suppose when we consider this particular W, as per Bst property, where it is going to be joined? It is going to be joined as a right child of B comma 41. That's what here you can clearly observe this. In figure B, you can clearly observe that W comma 60 is joined as a right child of B comma 41. Here in this particular figure, what can you observe? You observe that it satisfies the only Bst property. It satisfies the only Bst property, but it doesn't satisfy the heap order property. In order to satisfy heap order property, what we have to do? We have to perform some number of rotations, some number of single rotations. What are the rotations we need to perform? We need to perform. One is a right to left rotation. Second one is here we perform, after that we perform left to right rotation. Once we perform right to left rotation here, once we perform right to left rotation, then we will get this particular tree. After that, we are going to perform this left to right rotation. Once we perform the left to right rotation, we observe this particular one. Now, this satisfies both heap order Bst property and heap order property. Did you understand this?
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. Next. This is the example I discussed. Next one. Suppose if you want to perform remove operation, how do we perform remove operation? if you want to remove the node m,55 from the tree, first what we have to do? First, we have to find any node in the tree which has the required key m. Okay, if it has the required key, then we are going to delete that particular node logically. Okay, if that particular once it is deleted logically, later we are going to delete that particular node physically from the tree. In that particular process, here what we observe, here we identified this particular node m,55, right? After that, we are going to delete that, we are going to delete that particular node logically. That means we are going to set that particular flag field. Okay. Once it is logically deleted, how that node is physically deleted from the tree. In that particular process, in that physical deletion process, we need to maintain heap order property. Heap order property, to maintain heap order property, we are going to verify its children. Its children are d, 31 and n, 45. So to satisfy the heap order property, what we have to do? We have to make which rotation we need to perform. In order to satisfy heap order property, which rotation we need to perform?
First, we'll perform left and then right.
First, we need to perform this one, right? Right to left, right? This is right. And this is left. We need to perform right to left. When we perform right to left, this is the substructure of that particular tree. Did you get that? Okay. Here, what can you observe? Here you can observe that this particular logically deleted node has only one child. In that context, simply update its parent with parent of m,55. Then we will get this particular one. Did you get it? Now this particular one satisfies both Bst property and heap order property. Okay. Now, okay, till now I discussed about how to perform insert and delete operations on a particular tree. Here I considered only sequential implementation. Let us assume that such operation is just like binary search. Assume that here we implemented such operation but without using any logs. In that context, we don't find any difference between normal search and this particular log based, this particular concurrent search. Only difference is here we considered logical ordering in the search operation. To consider the logical ordering in the search operation, we are going to make use of predecessor and successor fields of the node. Right. Now, concurrent implementation. Right. Here I would like to discuss how to do the concurrent implementation by using logs. How to do the concurrent implementation by using logs. Here, these two methods, insert and delete methods, okay, both are designed, realized by using logs. Okay. Now, as per the discussion, okay, we are going to insert w,60 into the tree, into a concurrent tree. In that context, where w,60 is going to be joined, where w,60 is going to be joined.
The right side of Z.
w,60 is going to be joined as a right child of b, 41, right? Right child of b, 41. Here it is going to be joined, right? So that is why here we need to acquire the lock on this particular node. That is why we have to acquire the lock on this particular node. Are you with me? Are you with me? Do you have any? Okay. After that, once we acquire the lock, we inserted w,60 as a right child of b, 41. Once we inserted w,60 as a right child of b, 41, okay, it only satisfies the Bst property. It doesn't satisfy the heap order property. In order to satisfy heap order property, what we have to do? we have to perform some rotations. One rotation is right to left. This is right, this is left. We have to perform right to left. When we perform right to left, okay, which set of the nodes are going to be affected? Okay, fields of this node, this node, this node, all these three are going to be changed. Okay, so if fields of all these three are going to be changed, then what we have to do? We have to acquire the lock on these three nodes. First of all, we need to acquire the lock on these three nodes. Once we acquire the lock on these three nodes, then only we need to perform right to left rotation. Yes, now we perform right to left rotation. Once we perform the right to left rotation, this is the state. Okay, after that, now when you look at that particular one, it satisfies the only Bst property, but it doesn't satisfy the heap order property. To satisfy the heap order property, what we have to do? Again, we have to perform left to right rotation, right? Where we have to perform left to right rotation? At this particular node, right? In that context, which set of nodes are going to be affected? These three nodes are going to be affected, right? So we need to acquire the lock on these three nodes. Once we acquire the lock on these three nodes, perform left to right rotation. Once we perform the left to right rotation, then the state of the tree is like this. When the state of the tree is like that, or when the shape of the tree is like that, it satisfies both the properties, heap order property and Bst property. Then that particular thread come out from that particular operation. Did you follow that?
Yes.
Did you follow my explanation?
Yes, sir.
Okay. Next one. How to perform delete operation? Right. Here, what is our objective? Here, our objective is we want to delete m,55 from this particular trip. Okay. Suppose in that process, we are going to identify whether m exists in that particular trip or not. Whether do we have any node with the key value m. Suppose if it finds that particular node, if a thread finds that particular node, then it is going to log this particular node m,55 and its predecessor. That means when you look at the logical ordering of these nodes, right? What is the logical ordering of these nodes? When we traverse in order fashion, what do we get?
D, E, M, N, T, V.
Yeah,
W,
D, E, M, right? So in that context, what is the predecessor of M? E, right? Suppose when we look at this particular order, what is this order? What do we get? D, E, M, N, and so on. So when we look at M, predecessor of M is E. Here for this particular M, predecessor is E, successor is N. Okay. Similarly for E, predecessor is D, successor is M. In that way we have to identify, right? So for M, predecessor is E. So in that context, we are going to log both the nodes. Okay, why are we going to log the predecessor? Actually, in this particular implementation, we are maintaining both the orderings. Okay, what are those both the orderings? Actually, we are going to create any tree with a tree ordering layout. Okay, along with the tree ordering layout, we can maintain the logical ordering of the nodes. That means in order traversal of the nodes. Okay, when we maintain both, okay, we can use both the orderings while designing particular routine. Okay, here we lock the required node and its predecessor. Once we lock the required node and predecessor, we can think that it is a kind of simple linked list. Okay, when it is a kind of simple linked list, here we lock the predecessor and the required node. Then the required node can logically be deleted. That means here this particular node is logically deleted at this place. Once it is logically deleted, later we are going to think about how that particular node is physically deleted from that list or from the tree. In that particular process, what we have to do, we are going to think that how many nodes it has. If it has a single child, then it is simple and straightforward. Or if it has at maximum one child, that is very simple and straightforward. It has two children. In that context, we are going to perform some rotations, right, in order to satisfy heap order property. So in that context, we are going to log required nodes. When we perform right to left rotation, which nodes are going to be affected? When we perform right to left rotation, these nodes are going to be affected, right? So we are going to log these nodes and perform right to left rotation. Once we perform right to left rotation, this is the state of that particular shape of that particular tree. Okay, after that, we are going to update parent of D with as a parent of m comma 55. In that, once we update it, then we will get this particular one. Once we reach to that particular point, it satisfies both the properties and remove all the logs. Did you get my point?
Yes, sir.
Okay. Yes. In the insertion also, we use the logical ordering, right? Here, parent and both the logical ordering, both are same. Think about it. When we traverse in order, okay? So this one W comma 60 is going to be inserted between these two nodes, V comma 41 and Z comma 54. In that context, what may be the predecessor? Predecessor is W comma 60. That is why V comma 41 is going to be locked. Okay. Right. Suppose here our objective is we want to develop a logic for this particular trip implementation. In order to develop the logic for this particular trip implementation, concurrent trip implementation, we have to think about fields. What are the fields required for that implementation? Fields required is actual key. Here in this particular example, that is the English alphabet. Okay, after that, priority. Okay, next one. To traverse by using a tree ordering layout, we need left, right, parent fields. In order to traverse by using logical ordering layout, we need predecessor and successor fields. Okay, here we are going to log the nodes once by using tree ordering, once by using logical ordering, that is that successor log. This is a kind of name. Both are of type reentrant log. Okay, if a node is logically deleted, to identify that, we are going to use this particular mark field. Actually, if node is inserted, that means node is inserted by using Bst property, but it does not satisfy the heap order property. In that context, we are going to use this particular transit one field. Okay. Next one, in the context of deletion, if node is deleted, later we are going to verify it. Okay, that node is logically deleted but not physically deleted. In that context, we are going to use this particular transit2 variable. Okay, if you want, you can minimize this one. Actually, instead of this transit1, transit2 and mark, you can use the mark also. If you want to do the optimization, you can do that. Right. So this is the structure of the node. Okay. Here I gave the explanation for each one. Okay. Here, when you look at this particular return type is final. Once value is assigned to this particular key, that value is not going to be changed. That is why when you look at the return type of this particular key and priority is final. Okay, next one is volatile. Actually, when we look at here, we are going to actually to develop the logic based on transit 1, transit 2, and mark, because the different threads are going to access these fields. Okay, in that context, actually, when we put the qualifier volatile, what will happen is, if it is in the cache, actually that particular thread is not going to read the data from the cache. Instead of that particular one, either it is going to read the data from LLC or it from the main memory. In that context, we will get the correct data. This is the structure of that particular concurrent tree. After that, we have to think about what are the operations we want to perform on this particular trip structure. Okay, if you want to perform n number of operations, yes, we have to write n routines for that, right? Here, what are we are going to perform only 3 basic operations. They are contains, insert, and remove operations. Okay, contains operation returns true if X exists, otherwise it returns false. Insert operation does not exist. Okay, if X does not exist, then insert X into the tree with the priority P and returns true, otherwise it returns false. Remove, if X exists, remove X and return true, otherwise it returns false. These are the 3 basic operations are we going to perform on that particular concurrent tree. Okay, next one. How to achieve synchronization? That is right. That is also important, right? Okay. To achieve synchronization, here we are going to use 2 layouts. One is logical ordering layout. Second one is tree ordering layout. In the logical ordering layout, actually in this particular discussion, we observed that it uses predecessor and successor fields of a tree node. To acquire the locks by using tree physical layout, it's going to use the left, right, and parent fields of a tree node. Okay, that is the case. Next, after that, how to acquire the locks? That is important. Here, our objective is actually we never end up with a deadlock, right? At least we have to get some output. In that context, first, threads acquire the locks and tree nodes using logical ordering layout. Okay. Once threads acquires the acquire locks and tree nodes using logical ordering layout, here, what is the beauty of logical ordering layout? For every node, we have a unique predecessor. For every node, we have a unique predecessor. That is the beauty of logical ordering layout. In that context, if there is any contention between the 2 nodes, okay, with the help of that, we can eliminate one of them. Connection between 2 threads, we can eliminate that by using this particular one. Second one is threads acquire the locks using tree physical structure. Okay, by using left, right, and parent fields. Okay. Next, if a thread is unable to acquire a lock, okay, in that particular, actually, to perform a required update operation, either insert or delete operation, a thread supposed to acquire the lock and subset of the nodes. In that particular process, okay, if a thread is unable to acquire the lock, it releases all the locks that it currently holds. Then what will happen? At least we can avoid the deadlock situation. At least we can avoid the deadlock situation. But there is a possibility of live lock. What is the possibility of live lock? Suppose if one thread acquires the lock from root to leaves and another thread acquires the lock from leaves to root, then there is a possibility of live lock. Okay. Then also we don't observe any progress. Okay. We have to take care of how do we handle such type of cases? To handle such type of cases, while acquiring locks, we have to follow some ordering, right? Either from a root to leaves or leaves to root. Usually the better choice is if you follow the parent-child relationship, then it will be good. The next one. Once we designed algorithms for this concurrent implementations, actually, here I discussed how to develop algorithms for such type of concurrent operations. Here I discussed about concurrent insertion and concurrent deletion. Okay, I explained about how to develop concurrent search operations. Concurrent search operation is just like a normal BST operation. For that normal BST search operation, we are going to add some extra lines of the code. What are those lines of code? In that part, by using those extra lines of the code, we are going to verify whether the required node is present by using logical ordering or not, right? That is the extra lines we are going to add for that particular search routine. Now, here in the concurrent programming, we have to take care of experimental setup. Okay, we should have some idea about how the cores are going to be distributed. When we look at this particular, here I conducted the experiment on AMD Operand processor 6736. Okay, when we look at the speed of this particular one, it is this processor runs at 2.3 gigahertz and 64 GB RAM and 64 cores. When you look at those 64 cores, all the 64 cores spread across 8 NUMA nodes. Okay, so each NUMA node has 8 cores. Next, at the same time, actually, I already discussed, okay, for throughput of any concurrent execution depends upon cache hierarchy. That is why we should take care of how is the cache is distributed, what is the cache hierarchy of that particular server. We should have some idea. That is why here, when I look at that particular server, I observed that it has 16 KB of L1D cache and 64 KB of L1I cache and 2 MB of L2 cache and 6 MB of L3 cache. At the same time, if you want to know, you have to know the associativity of each caches. Next kind of operating system are we going to use it? Why do we need about operating system? And compiler environment. Suppose if you consider operating system, usually OS is responsible for thread placement. Okay, yes, where those software threads are going to be placed. Okay, on which core those software threads are going to be placed. And thread migrations. Okay, usually OS executes all these threads in a round robin fashion. Okay, when it executes those threads in a round robin fashion, so after a particular time interval, that particular thread is going to be suspended. After that, OS, if that again that particular thread pinned to the same core, then we'll get the benefit because the required data is available in that particular local cache. If the operating system pinned that particular thread to the different core, then actually again this whole data should be transferred from the one core local cache to the another core local cache. So much amount of time is going to be wasted, or at the same time cache coherence traffic is going to be increased. So that is why operating system also plays a major role. Okay, in that actually here while implementing all this concurrent implementation, we should take care of how that operating system do the thread placement. Next, at the same time, we have to know about version of the compiler. Okay, are we going to use JDK 1.7 or JDK 1.8 and so on? We should have some idea about version of that particular JDK. Okay, later we have to think about different kinds of workloads. What are the workloads? Actually, in the last session, I explained about particular workload, how to measure it. 50% contains, 25% insert, and 25% delete. Okay, just like that, here 50% contains and 25% insert, 25% delete. These type of workloads are called medium contention workloads. Here you can assume that contains operation is a lock-free operation. That means lock-free operation does not create any contention. Here, which operations create the contention? Only insert and delete operations. That means those two operations are the update operations. Those update operations create the contention of the data structure. So here, when we observe this particular one, number of contains operations is equal to the number of update operations. That is, we can assume that that is a medium contention workload. If number of contains operation is more than number of update operations, that is low contention workload. If number of update operations is more than number of contains, then it is called a high contention or workload. So we have to consider different workloads, and we are going to run that particular code for different workloads. Okay. Here we are going to measure the speed up of our concurrent implementation with the sequential implementation. Okay. How do we right? We have to consider while doing this particular speed up, while measuring this particular speed up, we have to measure with the best sequential implementation. We have to measure the this speed up with the best sequential implementation. Here, when you look at this particular one, when the number of threads is 64, okay, that means if we launch the 64 threads, and at the same time you can think that number of hardware threads is also 64, then there's no problem at all. Okay. Here we tested it for different key ranges. Here number of cases 2 times 10 power 5, that is 2 lakh, 2 million, and 20 million. Number of cases that. Here we consider the different workloads. Okay, this is high condition workload, medium condition workload, and low condition workload. Okay, these are the speed ups. This is the speed up. This is the average of 8 runs. Okay, usually we are going to run it around 10 times. After that, once we ran that particular experiment 10 times, we are going to remove the outliers. After that, we are going to consider the average of remaining 8 runs. Once we find the average of 8 runs, later we are going to calculate the speed up. Okay. Yes, from this particular figures, actually, what can you observe? You can observe that speed up increases with increase in the keys range. Speed up increases with increase in the keys range. What may be the reason for that? Suppose here keys range is 2 times 10 power 5. Here we observe the less speed up. When the keys range is 2 times 10 power 7, we observe the more speed up. The reason behind that is number of overlapping threads is very less as compared with that, because here size of the trip is big enough. In that condition, size of the trip is big enough, number of overlapping threads is less. Second one is speed up increases with increases as the contention decreases. Suppose here you can clearly observe this for this particular one. When we look at from left, when we scan that particular output from left to right, what can you observe? For this 2 into 10 power 5 keys, that is 2 lakhs. We observe that for high condition workloads, speed up is 6.42. For medium condition workloads, it is 7.5. For low condition workloads, it is 11.55. That means speed up increases as the contention decreases. Okay. Yes, these are the 2 observations from this particular concurrent implementation. Next, here I would like to just after that, if you want to compare this concurrent implementation with the state-of-the-art implementations, you have to consider state-of-the-art implementations, and you have to run all those implementations in your system or in your server, and you have to measure the speedups. Okay. And you have to compare the speedups. Next one. After that, here I would like to explain impact of locking objects. Impact of locking objects. Here we can. I implemented actually I developed this particular concurrent trip implementation. That is why I would like to discuss it. First of all, when you look at this particular concurrent implementation. Here, this particular concurrent implementation can be developed by using by considering different locking object. Here, I developed by considering 2 reentrant locks. Okay, one reentrant lock is for tree order, locking the nodes by using logical ordering. One more reentrant lock is to lock the nodes by using tree ordering. That is why I consider the concurrent trip with 2 reentrant locks. And instead, why should we consider 2 reentrant lock? We can develop the concurrent trip implementation by using 1 reentrant lock. Yes, to develop the particular code by considering only 1 reentrant lock, we have to be a little bit more careful. Okay, it takes time. Okay, right, when we do it by using, we can call it as that particular one is 1RL based implementation. Why should I consider particular reentrant lock implementation? Why can't we consider atomic integer locking object? Why it is atomic integer locking object? You can consider different locks. You can consider actually MCS lock. You can consider CLH lock. You can consider some other lock. Okay, if you consider different locks, you can compare your implementation for a different locking object. Okay, here I would like to show the speedups of this different locking objects. When I consider 2 reentrant lock, I observed less throughput. When I considered atomic integer locking object, I observed the better throughput. across the different workloads, and ranges of keys. That is the observation. Okay. When you look at this particular one, okay, here our interest is, yes, we are getting the better throughput when we consider the atomic integer. What may be the reason for that? Okay. How do we find the reasons for this particular speed up or better throughput? Algorithm is same. For all these three routines, three implementations, algorithm is same. Okay, but instead of for the same algorithm, we changed the locking object. Okay, for one implementation, we considered 2 RL based implementation. For other implementation, we considered 1 RL based implementation. For other one, we consider atomic integer based implementation. Yes, when we observe the results, we came to know that AA based implementation gives the better throughput as compared with RL based implementation, reentrant lock based implementation. Yes, to identify the reasons. Okay. We measure the reasons by considering the cache misses. How can we measure the cache misses? We can measure the cache misses by considering a perf tool. Okay, that is perform. Yes, by use when we consider the perf tool, we observed that AA based implementation gives the less number of cache misses as compared with RL based implementations. Not only that, do we have any other reasons to get the better speed up? To identify those reasons, okay, we calculated, okay, memory footprint. Okay, how much memory footprint RL based implementation takes? How much memory footprint AA based implementation takes? When we observe that AA based implementation takes very less memory footprint as compared with RL based implementations. Okay. Yes, we should actually here in the context of concurrent programming. Okay, throughput is somewhat when we are inversely proportional to the memory footprint. Not only that, okay, when we think about the time to acquire and release a lock, yes, RL based implementation takes more time as compared with AA based implementation. So suppose when we use atomic integer locking object, we observed that it can acquire the lock and release the lock within 26.3 nanoseconds. That is why we observed the better throughput. These are the reasons, okay, to find the better throughput. Are you able to follow?
Yes, sir.
Okay. Yes, suppose if you want to study further, okay, you can download the paper, Concurrent Trips and Impact of Locking Objects, that was published in the journal, New Generation Computing Journal. This is the reference for this particular paper. If you want, you can download that paper and go through it. All algorithms are presented in that particular paper. If you want, you can implement those algorithms. There are some comments. Okay, most probably I would like to address those comments after this next few slides. Next one. Here, efficiency of concurrent data structures. Suppose if you develop a concurrent algorithms for any data structure, okay, efficiency of that particular data structure depends upon how best the implementation uses the properties of the data structure. Suppose when we consider this particular concurrent tree implementation, if we don't consider that logical ordering, then actually for us it is very difficult to write lock-free contains operation. Lock-free contains operation. Suppose if we consider the logical ordering, then we can easily write the lock-free contains operation. We can handle all the corner cases. Then our job is much easy. Next one, the efficiency of concurrent implementation depends upon cache hierarchy. How L1 cache is shared, how L2 cache is shared. In L1 cache, instruction cache is there, data cache is there. How instruction cache is shared, how data cache is shared. We should have some idea. Based on that, that also defines the performance. Okay. At the same time, are we going to consider inclusive cache? Are we going to consider exclusive cache? Are we going to consider non-inclusive cache? That is, not only that, associated with the caches. Okay. Yes, it is 4-way associative or 8-way associative or 16-way associative. We have to consider it. Next, third one is synchronization. Okay. In the last session, I discussed about different types of synchronization mechanisms, right? We observed that lazy synchronization gives the better throughput as compared with optimistic synchronization and fine-grained synchronization. Anyhow, coarse-grained synchronization gives the very less throughput, right? Okay, when we compare the remaining three, we observed that lazy synchronization gives the better throughput as compared with optimistic and fine-grained synchronization. So which kind of synchronization technique is suitable for a given concurrent data structure? We have to think about it. Not only that, we have to think about synchronization object. Okay, which lock do we need to consider? Okay, do we need to consider reentrant lock? Do we need to consider next MCS lock? Do we need to consider CLH lock? Okay, yes, for some architectures MCS lock is a right choice. For some other architectures CLH lock may be a right choice. Okay, so we have to think about which lock is suitable for which architecture. Next, after that, we have to think about Operand System. Okay, how OS do the thread placement and thread migrations, because thread placement and thread migrations impact the performance of a concurrent implementations. Not only that, sometimes suppose if you want to execute a particular process and a particular core, what can we do? Suppose if you want to execute a particular process and a particular core, what can we do? We do thread pinning, right? How can we do the thread pinning? We can do thread pinning by using NomaCTL or task set. By using NomaCTL or task set. Yes, usually task set or NomaCTL is used to set the processes CPU affinity. What is CPU affinity? CPU affinity enables, okay, application or processes or threads, okay, to a specific core or range of cores. To a specific core or range of cores. That is important thing. Next one, in actually when we are using when we are doing this particular concurrent execution on a server. Okay, just now I showed an example. This particular concurrent tree executed on AMD Operand server with 64 cores, all the 64 cores spread across 8 NOMA nodes. Right. In that particular context, okay, how that particular OS do the thread pinning? We should have some idea about how that particular OS do the thread pinning. Here, when you look, when we remember that particular slide, that server's OS is sent OS. Okay, sent OS uses the scatter policy. In that scatter policy, what will happen is all the user threads are distributed to different NOMA nodes. All the user threads distributed to the different NOMA nodes using the some round robin scheduling policy. Suppose if you consider some other operating system, Sun Solaris. Okay, when we use Sun Solaris, what will happen is all user threads, okay, give preference to a particular NOMA node as long as number of user threads is less than number of hardware threads in a particular NOMA node. Number of user threads is less than number of hardware threads in a particular NOMA node. Then all those threads map to a particular NOMA node. In that context, we'll get the better performance. So suppose if you want to do this such kind of better performance on your particular server, what you have to do is you have to explicitly map all your process threads to the particular NOMA node when the number of user threads is less than or equal to the number of hardware threads of a particular NOMA node. Number of user threads less than or equal to the number of threads of number of hardware threads in a particular NOMA node. That is the case. Next one is hardware. How hardware plays an important role. Okay, here when we look at the hardware, we have to think about Okay, number of physical cores, number of logical cores. Okay, usually you people think that when you remembered my laptop configuration, I showed my laptop configuration as 4 cores and 8 threads. Okay, so that means that this laptop number of physical cores is 4, number of logical cores is 8. Suppose if we consider another laptop with only 8 cores, okay, 8 physical cores and 8 logical cores. That means there is no concept of hyperthreading. In that context, when you look at the performance of my laptop and others' laptop, definitely others' laptop gives the better performance. Okay, that is one thing. So we have to take care of those such small issues. Not only that, what is the type of the RAM? Okay, are we going to use DDR3 or DDR4 and operating voltage of that particular one? And data transfer rate of that particular RAM, we have to think about all those things. Along with that, we have to think about size of the cache, okay, how a particular hardware circuit is designed, and depth of the pipeline. We have to take care of all these things. Based on that, only we can analyze performance of a concurrent data structures or reasons for that particular throughput. Okay, otherwise it is very difficult to understand the reasons. Did you follow this lecture?
Yes, sir.
Okay, right. When you look at the references, actually for this particular concurrent programming course, if you want to refer any one of these textbooks, usually personally I prefer the first one, The Art of Multiprocessor Programming by Maurice Herlihy and Anil Shavit. Okay, and fourth one is also good. Not only that, if you want, you can download some of the papers from good conferences and journals, PPOP, HPCA, HPCC, SPA, PODC, and so on. Okay, and few journals, TOPC, TPDS, JPDC. Okay, you can download papers from those journals and read it. Go through that. Okay, that is about trees. That is about trees. Now I would like to give the break around 5 to 10 minutes. Okay, we'll be back at we are going to meet at 6:10. Right. Meanwhile, I would like to answer few questions. What are those questions? Yes, sir. Yes, sir. Right side. Okay. No questions at all. Yes. Anyhow, I will be available here itself. If you have any doubts, you can clarify your doubts. Otherwise, I would like to start a next session on different. How can we develop concurrent hash tables and concurrent skip list. Do you have any doubt? Hello?
No, sir.
Okay. Especially for this paper, I don't want to show any this one execution. Reason behind that is for this paper, all algorithms are available in that particular paper itself. You can straight away, you can implement those algorithms in any one of the programming language. You can check the performance. In the next session, I would like to show the executions of the concurrent skip list and hash tables. Actually, in the last session, I discussed about only 4 types of list implementation. I showed the execution of 4 types of list implementation, right? First one is coarse grained, fine grained, optimistic, and lazy. I didn't show that non-blocking implementation. Anyhow, I shared that particular code with you. Did you try?
No, sir. It's remaining.
Okay. Yes, please check that. You can use that particular non-blocking implementation. You can understand that.
large space of things
This
that
meeting is being recorded.
that different people are working in, and I'm happy that we could cover a large portion of this. Although, as Dr. Praveen was suggesting, that is I mean, we cannot cover everything in a few hours, right? So these are probably going to span more than one semester of topics if you want to really get into this. And therefore, it's highly recommended by all of us that if you are interested in this, please spend time, go back to these lectures, slides, and if you have any doubts, feel free to get in touch with us either on the group or in person, personally by email. We'd be happy to help out. Right. So I think there is some question by Nitin. Any advice you will like to give a newbie programmer starting in concurrent programming? Since as the presenter also mentioned that concurrent programming is an art. Any of you wants to take up that question?
So my only point, this pertains actually to any concept that you want to pick up, is learn the basics and keep practicing. There's no other way to beat this. So just right set of books to start with and practice.
At the same time, it is very difficult to identify the errors. Sometimes to identify the errors, I spent around 30 days or 40 days to rectify, to come out from that particular error. Okay. There is no other go. We have to sit with the code and identify the problems, the way in which we have to acquire the logs, and the way in which we have to release the logs, and how to consider different types of orderings. All these things you need to take care of it. Okay. At the same time, when we are working with a single thread code, this is a simple deterministic approach. After executing this particular one, you can predict the output. In the context of concurrent programming, okay, if multiple threads are going to work, you will get multiple outputs. Okay, you don't know due to which you face that particular issue. It is very difficult to identify in the non-deterministic setup. That is why we are going to call it is an art, not a science. Okay, you have to find your own reasons to rectify, to come out from that particular problem.
I just want to add to whatever the other speakers told. So with concurrent programming, yes, there are multiple threads and you are having different execution patterns. So I think the most important thing, as pointed out, was the log generation. So I think a lot of care should be taken to kind of properly present the log itself. So if we are just mentioning that we are here, then trying to find that statement itself, from which thread it has come and from which path it has come, it is going to be difficult. So putting a proper print statement or a log is very, very important. So I personally, I have worked on writing Verilog and system Verilog code before this. So they are quite similar, because like there will be execution, but they will be running in parallel and you never know from where it comes in. So there the savior was the clock. So you put the clock everywhere, clock number everywhere, the module number everywhere, and then you debug from that point of time. So, but here again, you don't have probably the support of clock. So I think the thread ID and putting all those information where it has come from is very important. Which particular location it has come from and what is the ordering, that to find out that, and then probably writing some scripts to kind of parse the log and to separate it out is probably what will be helpful. Yeah, that's the take from my side.
Thank you. I think there are a couple of more questions. One from TBK Rao. Could you please provide any playlist which has cache coherence protocols which were explained yesterday?
Sorry, which list?
Some playlist, maybe I think the question is about YouTube playlist. I think some video lectures.
YouTube playlist. Okay, I mean, probably I'll try to figure out if there is any playlist or so. I have never seen such playlist as of I know. But anyways, if there is any doubt or anything, they can reach on to me. I mean, they can send me a mail. I will revert back definitely.
Sure. Thank you, Dr. Devi Prasanna. Another question is, any NPTEL course to learn further?
For the same thing? Or
I think it is from Rishikesh, who is a different user. So I think it is in general that whatever these 6 different topics, well, not different related topics, but we have covered. So are there other additional materials, for example, any NPTEL course, which might be helpful for students to learn further?
I think no NPTEL course till now, right? No one is floated NPTEL course on concurrent programming. But if your students are really interested, we can float NPTEL course on this particular concurrent programming. If you are actually, if you want to practice problems, you can download programs from that Art of Multiprocessor Programming textbook or from some of the labs, Intel Parallel Computing Lab. You can execute it on your own. You will get some exposure. After that, if we have more number of students, if interested towards the particular NPTEL course, we are going to float it. If you're interested, definitely we'll float it in the next summer.
Okay, sir, sure. That would be great.
Okay, any other final questions by anyone? Students want to ask queries on WhatsApp group. That's what Nikhil Kumar is saying.
I think Google group may be a right option instead of WhatsApp group. What is your opinion on that? I actually strictly I don't have any opinion on WhatsApp group or Google group. I thought that Google group is much better than WhatsApp group.
Okay. So I think various speakers need to probably decide on this. We already have a Google group where all the speakers are present as well as all the participants. Yeah, Pranod is asking for a Google group. Yeah, but whether WhatsApp group is going to be useful or not, I think sometimes it becomes a little difficult to answer long. I mean, when there is a long response required, it becomes a little difficult on WhatsApp. Plus, it becomes a little more informal. So, if the speakers don't prefer, maybe initially we can work with Google Group if the discussion becomes a little too much or too verbose or more frequent. Then I think with the consent of the speakers, we can think about the WhatsApp.
Yeah.
Sir, may I know till how long it will be live, the Google groups, so to resolve the doubts and all?
Yeah, we'll keep the Google group live as long as Google supports free Google.
No, I am not asking like that, sir. It is available till 6 months or 3 months time period. I am asking.
I'm not sure if there is no activity whether Google disables the group.
At least 1 year.
Okay, okay. Thank you, sir. Thank you so much.
At the same time, actually, I'm interested to conduct one day workshop in the area of heterogeneous computing. Okay. Most probably, if you people are interested, most probably we may plan to conduct heterogeneous computing most probably in the next summer. Not now. Most probably, definitely in the next summer, we will conduct a workshop on heterogeneous computing. Good.
That will be nice, and NSM will be happy to support it. Pranod has given a suggestion that Google doesn't disable it, so that's a good sign. Any other concerns, questions?
Yeah, we would like to hear your feedback from you. I think feedback from the audience, participants. Would you like to give any public feedback?
Any feedback items are also welcome. What went well, what did not. Okay, we'll provide a feedback form. We'll take care of that from the NSM side. We'll collect feedback, anonymous feedback from everybody so that you can be honest. Sure, we'll do that. Thanks, Pranam. Thanks, KBK. We'll do that. All right, so that brings us to the end of this session. I would like to end this on a thank you note to all the speakers who actually are not only speakers, but they have been all the organizers as well. Dr. Praveen, Dr. Kalyan, Dr. Saurabh, Dr. Devi Prasanna, all of them have contributed to this great mini course, as we called it. Because we felt that the topics, it's not really a small workshop, right? It's almost like a teaching, 12 hours of rigorous teaching, and therefore we termed it as a mini course. And we were supposed to have it last year, but for unfortunate reasons, we couldn't conduct it last year. But this year, the speakers came together and we could conduct this. So I would like to thank all the speakers for their time as well as energy spent. And I would also like to thank the National Supercomputing Mission for sponsoring this event. And finally, I would like to thank all of you, diehard fans of HPC, diehard fans of concurrent programming, who could stay all the way to the end of this session. Thanks a lot, guys. And we hope to see you. I already see some of you from earlier sessions, so I'm sure some of you will continue in further sessions of the National Supercomputing Mission's Nodal Center at IIT Madras. Thanks a lot, guys. See you. Bye.
Thanks to the backend team.
Thank you.
Thank you.
Bye.
Thank you.
Thanks, sir. Bye.